This serves to attach the connecting rod and piston head while still permitting rotation. Together, these three components make the bulk of the piston assembly. During operation, the piston head is exposed to severe pressure due to combustion. These pressures vary greatly, but can be approximated by brake mean effective pressure, or BMEP. In standard operation, a typical BMEP would be about 120 psi, while a performance engine can see pressures of up to 230 psi. We will analyze both of these conditions and see if the piston assembly can operate reliably. To analyze our piston, I'm going to go ahead and create a new assembly. First, I'm going to select Insert Components and select the connecting rod. Next, I'll go ahead and select Insert Components again and drag and drop in the pin as well as the piston. Once we have all of the parts present, we need to mate them. I will use the default planes within each part to align them symmetrically. I will also use concentric mates in order to properly locate the pin. Now the part is fully symmetric. Let's take the time now, since our model is properly constrained, to take note of the overall weight of the assembly. First, I need to assign the materials to each component. The piston head and connecting rod are cast aluminum, while the gudgeon pin is 4140 steel. Now, we can go to the Evaluate tab and click Mass Properties. Here, the mass is listed as 1.22 pounds. Once we've taken note of this, we can go ahead and move on to our FEA simulation. Just as in the thermal analysis, I'm going to go ahead and go to Simulation and select New Study, except this time I'm going to be using the static condition. Once again, all we have to do is move down the list from top to bottom. The parts already have materials assigned since we analyzed the weight previously. This time, we will encounter a new part of the tree called Connections. I'm going to go ahead and right-click Connections and select Pin. For this feature to properly work, you'll need to select the inner and outer mating faces of the pin. In order to do so, I will hide the pin and select the inner face. Then I'll click the next condition, go into the feature tree, show the pin, and select the outer pin surface. I will leave all of the other settings as default and go ahead and press OK. I'll do the same procedure 2 more times for the other pin locations. Once I've established the proper connections, I need to set my fixture. I can go ahead and right-click Fixtures and select Fixed Geometry. Next, I will select the inner face of the crankshaft interfacing hole. Then, I'll go ahead and press OK. Next, I'll need to select the external loads. I'll right-click External Loads and select Pressure. Then, I'll select the top face of the piston head and set the pressure to 120 psi. Next, I can go ahead and right-click Mesh and create Mesh. At this point, we can go ahead and run the simulation. Once we have successfully run the simulation, we have a few options to represent the data. The default 3 options are stress, displacement, and strain. In the stress chart, you can see stress concentrations on the piston head and lower neck of the connecting rod. On the displacement chart, we can see the largest displacement in the piston head with a max displacement of 0.04 millimeters. In the strain chart, we can see the largest zones of strain are on the connecting rod. However, these values are actually negative since the rod is in compression. If we right-click Results, we can actually add in more charts. We're going to go ahead and select Define Factor of Safety Plot. I'm going to go ahead and select all bodies, press next, have a multiplication factor of 1, press next, and have a factor of safety distribution set to 1 as well, and then press OK. To get a better understanding, I'll quickly change the chart settings. Now we can see where the assembly is most likely to fail. To get a better understanding, I will right-click the chart and select ISO clipping. Then I'll check plot on ISO surface only and sweep from the largest to the smallest to give us a good idea of which zones are the most likely to fail. This area located here has the smallest factor of safety, which indicates that it is actually the most likely to fail. To get a better understanding of the other graphs, I'll go ahead and sweep through them as well. Another useful tool that I can use is the probe feature. I'll right-click the factor of safety chart and select probe. Then I'll click on the darkest color and read the value. The probe indicates a factor of safety of 10.2 at this point. Now, let's redo the simulation under high loads. We can simply right-click our pressure, select Edit, and change the value to 230 psi. Then, we can go ahead and run our study, and our new plots are up to date. By using the probe tool again, we can get a rough idea of what our factor of safety is now. This point indicates a factor of safety of 5.76. That's nearly half the factor of safety as before. Although the rod technically wouldn't break, a higher factor of safety would ensure a longer and more reliable lifespan. To achieve this, we can simply change our material type to 4032 aluminum. You can see here that the elastic modulus is much higher, coming in at almost 80 gigapascals, whereas the cast aluminum was just over 70 gigapascals. Now, we can go ahead and rerun the simulation. Once again, the chart that we want to focus on is the factor of safety chart. By using the probe feature, we can see what the factor of safety is. At this point, the factor of safety is up to 7.95. This material change has given us a significant increase in the performance of our connecting rod. We can also reanalyze the mass properties by going to Evaluate and selecting Mass Properties. Here we can see that the weight is still 1.22 pounds. Therefore, we have gained no additional weight, however we have gained increased performance. This type of simulation could give invaluable information to a competitive motorsports team. Both the weight and reliability of each component are determining factors in a team's success. This concludes the example of how to implement static analysis within SolidWorks simulation.